Hello YouTube. Today I wanted to do something a bit different. Something that I'm a bit more familiar with than electronics actually. Some simple geometry. So if you're doing trigonometry at school, you might have seen these values for the cosine. So you might wonder how you actually find these values. And these first two, they're a bit more familiar. This last one you probably won't see so as quickly at a high school. These can be proved with some simple constructions. But today I wanted to show you a more intricate, cooler, in my opinion, proof using abstract algebra, where you can also prove these more complicated cosine values with. So first let's talk about the definition of the cosine a bit. So if you have a triangle with a right angle, and you know this angle, which we'll call theta, then this is the hypotenuse, or the diagonal side if you're not crazy. And this is the adjacent side. The cosine, by definition, of this angle theta equals the adjacent side divided by the hypotenuse. So if we say that our hypotenuse is 1, then our cosine is just equal to the adjacent side. So if we vary our angle, then we can imagine this traces a circle. And the cosine is just the projection of this diagonal onto this line. So to do this, we have to know how to measure an angle, and you have probably seen it done with degrees. So an entire circle is 360 degrees. But I'm a mathematician, so I use radians. That's what's written down here. So this is just 2 pi. And mathematicians actually never use the word radians. They just know from context, oh, if it has a pi, it's in radians, probably. Why do we use radians? That's just the distance that an ant would have to walk if they walk on top of a circle. So if we look at some cosine values, the cosine of 0 is, of course, if this angle is just straight across. So that means a equals 1. So this is going to be 1. And the cosine of 2 pi over 4, meaning we divide the circle in fourths, is of course equal to the cosine of 90 degrees. And that is going to be equal to, if we put this upside, the projection is going to be 0. So this will be 0. So this proof is going to use abstract algebra, and when you hear algebra, you should of course be thinking complex numbers. Complex numbers are known to be a bit obtuse to people who learn them in high school, because they don't really know what their deal is, but as a mathematician you learn that they can be extremely handy, not only through algebraic constructions, but also because of all kinds of analytic constructions where you have to solve for functions with specific derivatives and stuff. In our case, we're going to use the algebraic structure of the complex numbers. And the way we're going to solve our cosine values is by looking at our circle in the complex plane. What that means is that every point on this plane is like an abstract type of number that can be multiplied and added together. And if you multiply them, there's a very good Free Blue One Brown video. You kind of stretch and rotate the plane. I'm not going to go into this too much. We're going to use one very nice fact about the complex numbers, and that is that they have what's called the roots of unity. If I write down x squared equals 1, then x can either be 1 or minus 1. However, if I write down x to the power 5 equals 1, then that can only have one real value for x, 1. But in the complex numbers, it can actually have 5 solutions. I'm not very good at drawing, but if you imagine that this is a perfect pentagram, where all of these numbers have distance 1 from the center, and this is just the number 1 on the complex plane, and these 5 points are called the fifth roots of unity. And they all have the property that if you multiply them by themselves 5 times, you end up with the number 1, because multiplication in the complex plane equates to rotation. And you can think about what all these other points do if you rotate them. Like this one goes here, and there, then there, and then there. Let's call this first one zeta. For some reason we typically use the Greek letter zeta for roots of unity. But we're just going to call this first one zeta. And notice that this one is zeta to the power 4. The other useful thing about this thing is that it is also a polynomial. So we can rewrite it as x to the power 5 minus 1 equals 0. And now we can think of this x not as zeta, but as a variable over any what's called a polynomial ring. That's going to be very complicated, and I'm not going to do all the proofs in this video, so you're just going to have to believe me. So the next thing about this polynomial is that we already know one solution, namely x is 1. And if you know anything about complex polynomials, is that you can separate every zero out of them. So we can actually divide this polynomial by the solution that we know. And then we get a simpler polynomial. And with simpler, I mean 1 lower degree. Instead of a 5th degree polynomial, it's going to be a 4th degree polynomial. And this polynomial is going to have exactly these 4 points as zeros of the polynomial. That's important. So zeta, zeta squared, zeta to the 3rd, and zeta to the 4th are the solutions of this polynomial. Okay. Next thing to notice, if we look at our zeta, and we look at the complex conjugate, that is the mirror image of zeta, if we mirror across the real line, which is of course this line in the complex numbers, then that's going to be exactly equal to zeta to the 4th. If we add a complex number with its conjugate, then we end up with a real number. In this case, we can write zeta plus zeta to the 4th is an element of the real numbers. And what's more, it's also an element of the field extension Q with zeta added to it. This is some complicated words, and you will see why this is going to be useful. It means that there is an analytic solution for this number. Final thing to notice about zeta plus zeta to the 4th is if we halve it, we end up exactly with our projection of zeta onto the real line, meaning that 1/2 zeta plus zeta to the power 4 is going to be exactly the cosine of 2 pi over 5. Now we've already proven that there's an analytic solution for this value. We've shown that it is in this field extension, but of course there's a good chance you've never heard of what a field extension is. let me continue with the rest of the proof and hopefully it will make more sense. So we've seen that our fifth root of unity is a solution to this polynomial, which is also known as the fifth cyclotomic polynomial. That's not on the test. This also happens to be an irreducible polynomial. That means that if we take this complicated field, which is a type of algebraic structure, then that is going to be isomorphic to, meaning it has the same algebraic structure as the quotients with our root of unity added. This just means you take all the quotients and you ask, if I multiply every quotient with this number and I take every combination where we multiply and divide and add and subtract, what are all the numbers that I can make? And that creates this algebraic structure. The real numbers are not in here, of course, it's just the quotients. If we only take the additive structure, there is a complicated theorem that says that this is also going to be equal, with just the additive structure, to a fourth degree vector space over the quotients, where our basis vectors are going to be exactly the number 1, our solution to the polynomial, the square of that, the cube, and that's already 4 basis vectors. So that's where we end. So we have our field extension, which is just all the quotients combined with all the possible combinations with addition and multiplication and division and subtraction that you can make with the fifth root of unity. So this is a combination. So this is a subfield of the complex numbers. And somewhere in this field lives the element 1/2 fifth root of unity plus the fifth root of unity to the power 4. And we've already shown that this is going to be equal to the cosine of 2 pi over 5. In order to solve what this is going to have to be, we're going to use the fact that if we take our polynomial that originally constructed our field extension, then we know that since this is a solution of the polynomial, zeta to the fourth is going to be equal to minus zeta to the third minus zeta squared minus zeta minus 1. Let's call this thing in here alpha. Then plugging this in alpha, we find that alpha is going to be equal to minus zeta to the third minus zeta squared. We don't get this one because it cancels with this, minus 1. And if we do some more algebra, we find that alpha squared, after reducing a bit, and this is an exercise to the listener, we find that alpha squared is going to be, what do I have here? Zeta squared plus 2 plus zeta to the power 3. If we add these two, we are left with just 1. This means that alpha squared plus alpha minus 1 is going to be 0, and we can simply solve this polynomial for alpha, and we know it's going to be a real number already, so we don't even have to worry about whether this is going to be a real number. And if we solve this, we find alpha, we take the positive branch, and that's going to be minus 1 plus the square root of 5 over 2. And then we simply plug that in there and we find our cosine value. So the reason why I absolutely love this proof is because it uses these complex numbers and this abstract algebra in such an intertwined, cool way to show this geometric property. If we run back our proof, we find that our little alpha was here, is our zeta and our plus our zeta to the power 4th. And then, of course, 1/2 alpha was this little piece of length. Now, I appreciate that most people are not going to know all the things about field extensions that I briefly went over. And so I wanted to talk a bit about what the purpose of this video is. And that is not to teach you about field extensions, but to get you interested in abstract algebra, because it's a really cool field, I think. So of course the next most important purpose of this video is so you can bedazzle your mathematical friends. And for that we're going to have to think about what the most complicated cosine value is that we can possibly derive from this. To find a very complicated value of cosine, let's first look at the 6th roots of unity, which of course make this nice hexagon. And the first thing we are going to notice is that 5 was a prime number, and that means that only the number 1 was a redundant 0, if you remember. But 6 is of course divisible by 3, and that means that if we already know the third roots of unity, we can simplify the cyclotomic polynomial of degree 6. And of course -1 is also a trivial root. So actually our 6th cyclotomical polynomial is going to be very simple, because it only has 2 roots, because these 4 are all redundant. The polynomial is going to be x squared minus x plus 1. Of course you can figure out what the cosine of this angle is, and it's very easy, it's just 1/2. Which is one of the things that I showed you at the start, and you can think about how to get that from this polynomial. And of course, the solutions are these complex numbers, but it teaches us how to get very interesting, complicated numbers inside of this cosine and still be able to figure out an exact solution. And that is to have a cyclotomic polynomial that has a lot of redundancies. And for that, we're going to have to look at the Euler phi function. Now, I'm not going to do a deep dive into the Euler phi function in this video. You can look it up on Wikipedia, for instance. I'm just going to show you the most complicated cosine that I came up with, and I'll challenge you in the comments to get a more complicated one. I'm sure it's possible. I'm going to cut to computer AGI now, because I did use some computer assisted proof. So after some toiling with quadratic equations or quartic equations, I found 4 zeros, and now the only thing to check left is that indeed this is our desired cosine value, and that seems to be the first one, and then maybe 7 times this, that is this zero, and then 13 maybe, 13 times this, yes, that's this zero, and then for the last one it's probably 11, right? Yeah, that's this one. So that's how you find wacky cosine values. I challenge everyone in the comments to find their own wacky cosine values and post them. I don't think you're going to beat 30 very easily. I think this is the most crazy cosine values that you can reasonably be expected to solve analytically. But I would love to be proven wrong in the comments. So that was the video, I guess. Bye. One last thing. This video was inspired by Ringen en Lichamen door H.W. Lenschijn, edited by Ben Monen, who was my teacher for abstract algebra. If you want to learn about field extensions, then something like this is really good. You can maybe find a PDF. I got it. Chapter 9, exercise 24 is the first part of the video with the cyclotomic polynomial 5. He very sneakily asks for the cosine without explaining how to actually do it, and you have to realize that it is in fact by making a complex number root of unity thingy. Very sneaky exercise.